Hey guys, welcome back to chapter 3. In the last video, we got to know electrons a little bit better, and we discovered that electrons behave like waves. When we send them through the double slit experiment, like in the Hitachi experiment, they will diffract, they will interfere, and they'll create this diffraction or interference pattern. So electrons behave like waves, right? Maybe not. In this experiment, we're going to take a look at something called the photoelectric effect. And it's going to help us to understand light and electrons in a slightly different manner. Maybe it's not so much like a smooth wave. So, spectrum of sunlight. So sunlight is light, right? But when we look at the spectrum from far away, kind of zoomed out, we look at it through a prism or a window, something like that. It looks like a rainbow, a continuous, pretty rainbow. But when we zoom in and take a look at the details, what we notice is that there's some dark lines kind of scattered throughout this continuum. So it's not this smooth rainbow that we would expect. There's actually something quite choppy going on in the middle of this. So scientists discovered this, and then they started to look at this thing called the photoelectric effect in hopes of explaining it. So here's the photoelectric effect. Am I going to ask you guys questions like recreate the photoelectric effect? No. But I do want you guys to kind of sit back and listen so that you can understand the conclusions that we come to at the end. So the photoelectric effect, while it really has nothing to do with electrons are involved. So in a photoelectric effect, we shine or emit electrons on a piece of metal. We shine light on a piece of metal. And when we do that, electrons are emitted, or they pop off. Okay, they come flying off that piece of metal. Okay, so what we're going to try to understand better is, does light behave the way that we think it should, and knock those electrons off in a way that's predictable, or does the light behave maybe a little bit differently? If light were to behave the way that we predicted, what we would see is that hitting a piece of metal with a high amplitude light, so that would be like a really bright light, or a light that has a short wavelength, which means it would have high energy, high frequency. So really bright light or really energetic light, it would be pretty easy to knock those electrons off, right? Opposite would be like a dim light or a very low energy, like a radio wave. If we were to hit a piece of metal with that, none of the electrons would come off. Okay. Now, if we were using a low energy dim light, eventually an electron would pop off. So those waves would continue to crash into the metal, and eventually, after crashing long enough, the electron would come off, much like beach erosion. Or you can think of it like hammering a nail into a piece of wood. Even if you hit that nail very, very lightly, over the course of many, many taps, that nail would eventually drive into the wood. Understanding that first prediction, so a high amplitude light is a very bright light, high intensity. So we can think about this as like swinging a baseball bat, right? So if I were to swing a baseball bat at, let's say, a tree really hard, the bark on that tree would probably come flying off, okay? Same thing, high amplitude light, electrons are going to come flying off. If I were to just barely tap a tree with a baseball bat, not swing very hard, the bark may not come off, or maybe just a little bit would come off. So that would be our analogy for the amplitude. Analogy for the shorter wavelengths, remember this has to do with the energy, so high energy, low energy. So we could think of a short wavelength, high energy. We could think of this like throwing a lacrosse ball at a glass window. So that lacrosse ball flying at a glass window, probably going to break through it, right? Probably going to go right through it. A longer wavelength, lower energy light. Maybe it's like a ping pong ball. So we throw a ping pong ball at a glass window. The likelihood of it crashing through is a lot lower. Okay. So that's how we would predict light to work, kind of based on the physics that we understand. If light is a wave, this is what we expect. But reality wasn't what we expected. What we found is that the electrons coming off were independent of amplitude. It didn't matter if I swung really hard or if I swung really soft. If I was not using the correct bat, electrons would not come off. If I was using the correct bat, the speed of that swing didn't matter. A soft swing with the correct bat, electrons would come flying off. And that's explained in this graph right here. So let me just set this up and then we'll understand it. Across the bottom, we've got frequency of light. So that's like the correct bat, okay? So down here we've got low frequency, up here we've got high frequency. On the side we've got our rate of electron ejection, so the rate at which those electrons are coming off. So are they flying off, are they trickling off, are they not coming off at all? So down here where this line is flat, that is no electrons coming off. Up here at the top is all of the electrons coming off. So what we see is two lines. The red line is a low intensity light, so low energy, that's our ping pong ball. Oops. The blue one is a high intensity light, that is our lacrosse ball. Okay. If we pick wrong frequency of light, it doesn't matter if it has a lot of energy or if it has just a little bit of energy. It doesn't matter if I'm swinging soft, swinging hard. None of those electrons are coming off, okay, if it's not the right frequency. And then all of a sudden, when we pick the correct frequency of light, in that moment, all of the electrons are ejected. It doesn't matter if I swung soft. It doesn't matter if I swung hard. All the electrons are coming off in that moment. And then if I change the frequency of light again, we do not get an increase. That actually stops ejecting electrons. It levels out or stables out. Okay? So this is what we mean by independent of amplitude. It doesn't matter how hard I swing that bat. If I'm swinging the wrong one, none of them will come off, flat line. If I'm swinging the correct bat, all of the electrons will come off, no matter how hard I swing that bat. Okay. We also find that it is independent of frequency. So that idea of like tapping a nail and eventually it drives into a piece of wood, that doesn't happen here. It either drives in the wood on one swing or it does not, and there's no like duration of shining this light that can change that. Okay. So we predicted two outcomes, and reality tells us that the outcomes are very different than what we predicted. So we predicted light is going to behave like this kind of continuous, smooth wave. But it turns out that light actually behaves much differently. So the difference is this idea of quantized versus continuous. So here we see a ramp gradually going up, and we see a set of stairs going up. The ramp is going to be our analogy for continuous. This is what we thought light behaved like, a continuous, smooth wave going out. But it turns out that light behaves more like these stairs. There's little packets of energy associated with light. So this stairs is our example of quantization. There's these discrete little packets, and there's not a continuous smooth transition. So this stair is one packet of light. This stair represents another packet, and another packet, and another packet. So this idea of smooth light is what we expected to see in that sunlight. Smooth rainbow. But what we actually saw was something much choppier. We saw those black lines kind of throughout. And after doing the photoelectric effect experiment, we see that those black lines are caused by these little packets of light called photons. So, the guy that discovered this, we'll see him in just a second, was this guy called Max Planck. So Max Planck introduced this idea that light is quantized or has little packets of energy. Planck's work was extended by Einstein, who then started to look at these packets of light and started to assign an energy associated with these packets. Okay. So Planck and Einstein kind of worked together to form this idea of what we now know as the quantum theory, that light, and as it turns out, electrons are little packets of energy that behave kind of like a wave. Very, very different. So here is of that formula. We can calculate the energy associated with these packets of light or packets of electrons. So E here stands for energy. That's what we're going to solve for. This H is something called Planck's constant. And this V is the frequency of the light that is emitted. Okay. So we're going to use the formula for the speed of light, which was introduced earlier. But here I just kind of rearranged it so that I solved for frequency, because frequency isn't something that we can measure easily. But we have this constant c, that's the speed of light. And then we have this wavelength down here at the bottom, and wavelength is actually something that's much easier to measure. So by doing a simple variable replacement, so I'm going to take frequency, I'm going to replace it with these two variables, we get the following formula. The energy associated with these little packets of light can be calculated by using Planck's constant given, speed of light given, and then wavelength, which is something we can measure. Okay. If you're taking my online course, you will have an atomic spectrum lab where you guys are going to look at emission spectrum, and you're going to calculate some of these lines that get emitted. So that's going to be something that you guys do in the lab using that formula that we just discussed. So how does this connect to electrons? Where do these like lines come from? So electrons occur in around an atom, and we'll talk about how that's organized and what these ends and whatnot meet a little later. But what we need to know right now is electrons have what we call a ground state, a home that they reside in. There are things that happen that can excite these electrons. They get excited and they jump up to another energy level or to somebody else's house. They get really excited and they just go away. Eventually, things will calm down. They have to come back to their home. And when they come back to their home, they're going to emit some energy in the form of light. So here's my little electron. It's going to settle down. It's got to get rid of some of that energy that it absorbed. And when it gets rid of that energy that it absorbed, it's going to emit it in the form of light. Okay. When that happens, what we observe are these little lines at very distinct wavelengths. So this is representative of one electron that's relaxing. This represents another electron, another electron, another electron. So they're emitting these very distinct lines, and we can calculate the energy associated with those lines. So let's take a look at an example. So here's an example. What is the energy of a photon of light from the largest quantum dot? The wavelength associated with that photon is 640 nanometers. What is the energy of 1 mole of those photons? So the formula that we're going to use is going to be the one we introduced a couple slides ago. Energy equals Planck's constant, speed of light constant, divided by wavelength. Go ahead and pause this video and see if you can calculate that. Quick tip, make sure the units match. All right, anytime I solve a problem like this, I'm going to take inventory of what I know and see what it is I'm trying to solve for. So I'm just going to rewrite my formula up here. All right, so inventory, I've got energy, I've got Planck's constant, I've got speed of light, and I've got wavelength. So energy is what we're solving for. Planck's constant, something that's going to be given. It is 626 times 10 to the negative 34 joules times seconds. For the speed of light, we've got 3.0 times 10 to the 8th. The units on that are meters per second. And then we've got our wavelength, which is measured and given to us in the problem as 640 nanometers. So the one thing that we have to be careful here is we have to make sure that all of our units are matching up. So see that my unit for time is seconds and seconds, but my unit for distance is meters here and nanometers down here. That can't happen. We have to have those units match. So the first thing I'm going to do is I'm going to change the units from nanometers to meters. So this is a simple unit conversion. I'm going to start with 640 nanometers. I got nanometers on the top, So nanometers are going to go on the bottom because that cancels, and we'll have meters on the top. In 1 meter, that is 1 times 10 to the 9th nanometers. So I'm going to multiply across the top, divide by the bottom, and we get 6.4 times 10 to the negative 7th meters. Okay. So just a quick unit conversion so that my units match. So I'm going to replace this over here with 6.4 times 10 to the negative 7th meters. So once my units are in line, now this is a quick plug and chug problem. Plug it into the equation, chug our way through it. So I have energy equals Planck's constant, so 6.62, that's really sloppy, sorry. 6.626 times 10 to the negative 34th joules times seconds, multiplied by the speed of light, which is 3.0 times 10 to the 8th meters per second, and all of that divided by our wavelength, which is 6.4 times 10 to the negative 7th meters. So here's why it's important that our units are the same, because we're going to see some are starting to cancel out. I've got seconds on the bottom of a fraction, seconds on the top, so those cancel. I've got meters on top and meters on the bottom. Those cancel. The only unit that's left in this problem is joules, which is good news because that is the unit for energy. Now, to solve, we multiply across the top, divide by the bottom. So 6.626 times 10 to the negative 34th. 3.0 times 10 to the 8th. Divided by 6.4 times 10 to the negative 7th. And we get 3.10 times 10 to the negative 19th joule. So the energy associated with that photon of light is 3.10 times 10 to the negative 19th joules. So in this video, we looked at the fact that light isn't this continuous wave, neither are electrons. We saw that they're like little packets of energy, and then we were able to calculate the energy associated with those packets. In the next series of slides, we will see how this idea of quantum or quantized started this whole new realm of physics, a whole new division of physics called the quantum theory or quantum mechanics. Hope you guys found this helpful.